Well, hello everybody, Dave here, and today we're going to do our second lesson in electric circuits, and we're going to deal with a big one here because we're going to learn all of Kirchhoff's laws. You'll see that we go through the derivations, and through those derivations we'll do an example problem to hopefully make sense of what's going on with these laws and how they work. When we wire a circuit, there's essentially two ways that we can do so. You take a look at the one on the left, we have a battery and we have this wire that goes all the way around and it never branches off into another direction. Well, we call this a series circuit. And by series, we just mean that each of the digital devices is connected one after another after another. Another way to think about it is when it comes to current, the current only has one direction that it can travel and one pipe that it can go down. So there's no way that the current can break off of a series circuit because there's no other places for it to go. It has one path and that's it. Compare that to the diagram on the right. We have a battery, but now this time look what we've done. We've taken the light bulbs and we've hooked them up in what's called parallel. And you'll notice that now the current has multiple directions that it can go. When it gets to that first point there, some of the current will have to travel down to the light bulb, but some of the other current will actually have to continue traveling down the original path it's on. And so what happens in a parallel circuit is this split in current, which is happening at what's called a junction, changes the discussion that we have when it comes to things like current and voltage and resistance. So in order to approach circuit problems, we're going to have to understand the schematics that we see. And for that, we have to get into the symbols at play. And so on the right, you can see the various digital devices and the symbols that will represent them. At the top, you see the DC voltage source or battery. Now, it depends upon the question, and sometimes you will see it drawn like that where it looks like there's multiple long lines and short lines, but you'll also see the diagram like at the bottom there that just shows one long line and one short line. This can represent a battery. It can also represent a cell in a battery. So for example, if we have 3 AA batteries, we would represent 3 AA batteries connected as a diagram similar to the one up top. If we just wanted to say that the total voltage of the battery was 6 volts and they don't care about this split up in cells, then the diagram on the bottom will do just fine. The point we're trying to make here is whenever you draw a battery or a voltage supply, the long line has to represent the positive terminal and the short line has to represent the negative terminal. So always make sure that they were very obviously different, because this is going to help you understand the direction of the conventional current. Until now, we've essentially focused on the electron flow of circuits because that's helping to explain the physics. But now that we're getting into the circuit problems themselves, we are going to focus exclusively on this idea of conventional current. So the easiest thing to understand here is the conventional current will go from the negative towards the right to the positive and away from the positive to the right. That's the easiest way to understand the direction of the current based upon this battery diagram. The symbol for a resistor is this squiggle that you see on the right. Now, I had a professor in university that was very particular in that there had to be the 3 valleys and the 3 peaks. And I encourage you strongly to be as specific and meticulous as you can in your circuit diagrams. So a little bit of extra time to make the squiggle look exactly like that is a great idea. The next ones are actually going to be meters that we use to measure current and voltage, known as a voltmeter and ammeter. And it's as simple as a circle with a V in it or a circle with an A in it. And you'll notice again that it is directly in line with the circuit. You'll find out that the way that we hook these up is actually a little different. The next symbol is a switch, and that's as simple as 2 dots in the line that is pulled up a bit, so that we recognize again that the circuit is broken, but it does have the ability to be closed. And the final one at the bottom there is a light bulb. And the light bulb, I've seen it as an X in a circle, but the historical picture of a light bulb is actually this one little loop inside the circle. Whichever one you want to use is going to be more than understood. So this voltmeter and ammeter thing comes down to our understanding of what it is they need to read. We want to use an ammeter to read the current of our circuit. So it would make sense that we want to put an ammeter in series with that circuit. Why? because we want to make sure that the current actually flows directly through it. If it didn't flow directly through it, then what would it be measuring? Well, with a voltmeter, we actually hook it up around the digital device that we're trying to find the voltage of. And this comes down to the idea of understanding that we are trying to connect it to the terminals of the digital device itself. So we have it hooked up to the positive terminal and the negative terminal. If we put this around the battery, then we would have it hooked up to the positive terminal and negative terminal of the battery, which means that the voltage read would be the voltage of the battery itself. Now there's some important theory to consider when we're talking about ammeters and voltmeters when it comes to the idea of resistance. If you think about what an ammeter is supposed to do, it's supposed to read the current by allowing it all to flow through. Well, it wouldn't make much sense in theory if there was some resistance associated with an ammeter. So when we talk about an ideal ammeter, we consider it to have zero resistance. At the other end, with a voltmeter, we have it hooked up to a digital device. We don't want any current to travel through the voltmeter. We want all the current to travel through the digital device so that we can measure the voltage associated with that digital device. Because of that, in theory, the ideal voltmeter is considered to be an infinite amount of resistance. Now, is this a reality? No. But at the same time, is it close? Absolutely. But for the sake of our circuits in these problems, you're always going to assume that all of the current will travel through even when a voltmeter is hooked up, and all the current will travel through the ammeter with no resistance associated. So now we are going to take a look at different types of circuits and how we can come up with some rules to apply to all types of circuits. These rules are known as Kirchhoff's laws. So with a series circuit, we can get into what happens when we have multiple digital devices hooked up. And we've already talked about the current in that there's only one path for the current to travel, which means that no matter where we measure the current in a series circuit, it should read the same amount. Again, there is a conservation of charge taking place here, which means that charge can't be lost anywhere. There is an energy argument here, but again, energy is still conserved within this circuit. So what that means is if I put the ammeter between the battery and the first bulb and the second bulb with the third bulb, or third bulb and the back end of the battery, all of those should read exactly the same current. When it comes down to voltage, again, we are discussing the energy associated with the particles when they leave the battery, and what's going to happen is some of that energy is used on the first digital device. The particles will leave there with less energy, but they will still have energy to use in the second device, and whatever energy they have left, they're going to get to use in the third device. So the idea behind this is the voltage in series is going to be the sum of each of the voltages on bulb 1, 2, and 3. We refer to this as a voltage drop. So again, it is these collisions with the conductor that is allowing for this energy to transfer from the particles to the digital device itself. So if we take our series voltages and we consider these according to Ohm's law, well, the total voltage coming out of the battery would just be the total current times the total resistance, and the voltage on each of the bulbs would just be the current on that bulb times the resistance of that bulb. But we've already determined that the current is the same at the beginning as it is at the end. And what that means is mathematically we can cancel the current and we are left with the resistance in series to be the sum of the individual resistances in that circuit. And so that last statement there is the resistance in series is the mathematical sum of all the resistance elements in the circuit. This is specific to a series case. You may also see, by the way, the words either effective or equivalent when they're talking about the resistance. And really that's just fancy language for the total resistance. So the idea being that if we take the sum of the resistances and we get the total resistance, that is the equivalent resistance as if we had a circuit with one resistor of that value in it alone. Let's take a look at what that looks like at practice. So we have a series circuit as seen on the left, and we want to find the total resistance. Well, we know that that's going to be the sum of the individual resistances, which is 1 plus 2 plus 3, which is equal to 6 ohms. That means that the 6 ohms equivalent resistance is if we had this circuit but with one resistor in it, it would take a resistor that is 6 ohms to have the resistance equivalent to the current circuit you see before you. That's what equivalent resistance means. Now, if we're looking for the current, we know the total voltage is 12 volts. We now know the total resistance, so we can simply use Ohm's law and solve for I to get 2 amps. C now asks a question that textbooks love to ask. What is the current across each resistor? This is challenging your understanding of series circuits, but we just need to remember that whatever the total current is in the circuit, that is going to be the same current across each of the digital devices. The answer to D, however, is going to be different because each of these devices has a different resistance. So if we look at the voltage across the 1 ohm resistor, well, that's just V is equal to IR. We know I is 2. We know R is 1. So the amount of voltage across that 1 ohm resistor is 2 volts. You can see for the 3 ohm and 2 ohm resistor, we're doing very much the same calculation. You know that you have done something correct when you notice that 2 volts plus 6 volts plus 4 volts is equal to 12 volts, which is the total voltage for the circuit. So as long as you understand that the current is the same in a series circuit, how to find the total resistance and how to find these individual voltage drops on the digital devices, then a series circuit should be a straightforward circuit for you. Parallel circuits are a little trickier because we have to understand what happens to the current. If you think about a water pipe, when a water pipe splits, some of the water is going to travel down one part of the pipe and the rest of the water is going to travel down the other. When we bring those two pipes back together at a later time, what ends up happening is the full amount of the water will now flow down the pipe again. This is exactly what happens with electric current. If we look at the conventional current leaving the top of the battery, when it gets to that first junction, some of the current is going to travel down the path towards the light bulb, and the rest of the current is going to travel towards the other 2 light bulbs, in which case that amount will split again, and then when it goes around the loop and it gets back to the junction on the other side, the current will come back together, and then when it reaches the other junction, the rest of the current will come back together, so that the total amount of current that we started with will be the total amount of current that we finish with at the end of the circuit. If you look at the diagram again, you'll see 3 moving dashed lines. You have the green dashed line and the blue dashed line and the pink dashed line. Well, these are actually representing 3 different loops in the circuit. But you'll notice that all of these loops are connected to the terminals of the battery. What that means is regardless of which digital device we're looking at, they are all connected to the positive and negative terminal of this battery. What that means is whatever voltage is on that battery will be the voltage that is across each of these digital devices. So unlike a series circuit where the voltage splits up, because these are all hooked up to the terminal ends of the battery, they all possess the exact same voltage that the battery is providing. Now, if we have a circuit where there is another device in series before you reach the parallel ends, we would have to consider the parallel devices separately from the series device, and we would have to figure out how much voltage is dropped on that series device first. Whatever voltage is left would be the voltage across the parallel circuits. So you can tell that parallel circuits are a little more tricky. So with an understanding that the voltage is the same across all of the digital devices and that the current actually adds up at the junctions, then we can apply Ohm's law and come up with a relationship for the resistance in parallel form. We know that the current total is equal to the sum of the currents, and we know that with Ohm's law we can determine that current is equal to the voltage divided by the resistance. So the total current is going to be the total voltage divided by the total resistance, and then each of the individual currents can be written as the individual voltage divided by the individual resistance. Well, we know that the total voltage is going to be the same as V1 and V2 and V3, and so much like the series circuit where we could cancel out current because it was the same, with a parallel circuit we can cancel out voltage because they are the same. And what we end up with is this inverse relationship that 1 over the total parallel resistance is equal to the sum of the inverses of each of the resistances. You've got to be careful when you use this equation, because what a lot of people do incorrectly is they will simply flip the fractions to come up with the parallel resistance is equal to R1 plus R2 plus R3. That is absolutely not the way to do it. Instead, you would put brackets around 1 over R1 plus 1 over R2 plus 1 over R3, and then take that sum and invert that to get your total parallel resistance. It's important to understand that this resistance is the equivalent resistance of all of the parallel branches of a circuit. If we use this equation and we find what RP is, that would mean that if we had a circuit and we put one resistor of a certain value of RP into it, that would be the equivalent resistance of whatever circuit that you have and however many parallel branches that you have. Something exceptionally interesting about this is the fact that the equivalent resistance will always be less than the individual resistors in their parallel branches. So if we have a 4 ohm resistor and a 6 ohm resistor, and both of those are in parallel, the equivalent resistance will always be less than either of those devices. This is an important thing to recognize when you're calculating parallel resistance. So let's do an example to understand how to use this equation. So we see a diagram to the left and we see that we have these 3 resistors and they're all in parallel. And the question is, what is the total resistance of the system? So again, we use this inverse relationship. 1 over the parallel resistance is equal to 1 over 5 plus 1 over 7 plus 1 over 9. Well, when we do the sum of those fractions, we get the value of 0.454. When we invert that value, or 1 over the answer, what we end up with is 2.20 ohms. So this is exactly what I was stating before. If you look at the resistors in parallel, you see that it's 5 ohms, 7 ohms, and 9 ohms, but the equivalent resistance is one resistor that would be 2.2 ohms. So if we added another resistor to this parallel structure, we would actually lower the equivalent resistance of the circuit even more. So for B, they ask, what is the total current? So from here, the parallel resistance is actually the hardest part, because now we have the total voltage, we have the total resistance for this circuit, so we can simply use Ohm's law to find out that it's 3.64 amps. For C, it's asking for the voltage across each resistor. Well, don't be confused by this. When we look at the circuit, we see that there's no other devices that voltage could drop on, which means that the voltage across each of these resistors has to be equivalent to the total voltage of the system. In this case, each of these resistors has 8 volts across it. When we want to find the current on each resistor, this is where it gets a little tricky, because we have to apply Ohm's law, but we have to apply Ohm's law to each of the individual resistors. So you'll notice that we found the current for the 5 ohm, 7 ohm, and 9 ohm resistor, and we got these different values. If we add these 3 values up, what we should get is 3.64 amps. Now, there is something important here that I want to point out. If you notice, we have 1.6 amps on the 5 ohm resistor, and then the values of the current actually go down. This speaks to a pattern that I want you to recognize, which is more current will always go down a path with less resistance. So you'll see that the path that had the most resistance also has the least amount of current. This is an important pattern to recognize, because the old adage is current will travel down the path with least resistance. So if we actually hooked up a wire in parallel with the rest of this circuit, what we would notice is that all the current in theory would want to go down that wire, because it would have no resistance in theory. This is something known as short circuiting. So again, current going down the path of least resistance is an important pattern to recognize in circuits like this. So there you have it, everybody. We went through the derivations of Kirchhoff's laws, both in series and parallel circuits, and we took a look at a couple of examples of how those laws actually are used. I hope it made sense, and best of luck with the practice problems. We'll see you again.